MCV 4U1 Chapter 5, Session 7. In this session, we work on Section 5.3, Optimization Problems Involving Exponential Functions. In earlier chapters, we considered numerous situations in which we were asked to optimize the given situations. As we learned, to optimize means to determine value of variables so that the function representing quantities such as cost, profit, area, number of objects, and so on can be minimized or maximized. In this section, we work on optimization using exponential function models. Example 1. The effectiveness of studying for an exam depends on how many hours a student studies. Some experiments show that if the effectiveness E is put on a scale of 0 to 10, then ET equals 0.5 times 10 plus T e to the power of negative T over 20, where T is the number of hours spent studying for an examination. If a student has up to 30 hours for studying, how many hours are needed to maximize effectiveness? Basically, we are looking for the maximum value of effectiveness function, ET, when T is greater or equal than 0 and is smaller or equal than 30. We take the derivative of the function by using constant rule and product rule. Derivative would be 0.5 times derivative of inside bracket. Derivative of 10 is 0. Derivative of T e to the power of minus T over 20 can be found using product rule. Therefore, the derivative is 0.5 e to the power of negative T over 20 times 1 minus T over 20. If we set it to 0, we have T equals 0 as the only critical number. We use algorithm for finding maximum minimum of a function on a closed interval by finding the value of E at 0 and 30, the endpoints, and 20. We'll see the maximum effectiveness is 8.7, and it is when the student studies 24 hours for the exam. Next example, a mathematical consultant determines that the proportion of people who will have responded to the advertisement of new product after it has been marketed for T days is given by f of t equals 0.7 times 1 minus e to the power of minus 0.2 t. The area covered by the advertisement contains 10 million potential customers, and each response to the advertisement results in revenue to the company of 70 cents on average, excluding the cost of the advertisement. The advertising cost is $30,000 to produce and a further $5,000 per day to run. A. Determine limit of f of t as t approaches infinity and interpret the result. We know limit of e to the power of minus x as x approaches infinity is 0. Therefore, limit of e to the power of minus 0.2t as t approaches infinity is 0. That means limit of f of t as t approaches the infinity is 0.7. And this means if the advertising is left in place forever, 70% of the population will respond. Part B, what percent of the potential customers have responded after 7 days of advertising? We are simply looking for f of 7. It is 0.53, and it means about 53% of the population has responded after 7 days of advertising. Part C, write the function PT that represents the average profit after T days of advertising. What is the average profit after 7 days? Profit is revenue minus cost. Cost of advertising is 30,000. The fixed cost plus 5,000 T if it runs for T days. Revenue is basically 10 million times F of T times 70 cents. By subtracting these two functions, PT would be 4.9 times 10 to the power of 6 times 1 minus e to the power of minus 0.2 t minus 30,000 minus 5,000 t. And average profit after 7 days is 3,627,000. It can be found by simply plugging t into profit function. Part D, for how many full days should the advertising campaign be run in order to maximize the average profit? We are looking for maximum of the profit function. Assume that an advertising budget of $200,000 is in place. We have 200,000, therefore 30,000 plus 5,000 T, which is the cost of advertising for T days, must be smaller or equal than 200,000. From here we have T smaller or equal than 34. Therefore we are looking for the maximum of PT on a closed interval 0 and 34. We take the derivative of PT, set it to 0, and solve a system exponential, a simple exponential equation, and we find T is approximately 26. We calculate the value of PT at 26, 0, and 34. And we see when T is 26, we have the maximum profit, which is $4,713,000. In summary, we know optimizing means determining the values of the independent variables so that the values of a function that models the situation can be minimized or maximized. The techniques used to optimize exponential functions model are the same as those used to optimize polynomial and rational functions. To understand the concepts in this section better, next session we are working on questions from page 245 and 246. 5.3, question 1, part B, question 5, question 6, question 10 and 11. Thanks for watching.